Sweet. I think we're live. I think we are live. Yeah. Hey everyone. Yeah. So, don't worry. I've been working on. I met a new friend today, and we've been working on. Some little issue that they had, but it's good now. I think the app is building a bit, and yeah. So let me get this thing open, and we can go back and build what we had yesterday. Documents eng cd ls, what is it, cd USB CDC host experiment clear, git branch again, git checkout master. Okay, cool. So we worked on yesterday. What did we do yesterday? We worked on a USB CDC host application. And hey Tomas, Bartlome is around. Welcome. Yeah. So yesterday we worked on a CDC host app, and let me know if my audio is working okay and everything's working okay, man. So a recap. We made a host application on our computer to communicate with a CDC host device that is running on this STM32N6 application board. The actual board doesn't really matter because we're just using anything that has a host, a USB peripheral. And I'm gonna go and I'm gonna do a picocom -b, and I will do 11.5.200, and I will want to open dev CDC-ACM 0, I think. And I think if I reboot this, we get, yeah, so it boots. So we have a, like you can see, well, thank you. So we have a CDC host application, a CDC device application that is running on the board. And what we wanted to do yesterday was actually build a CDC host application now that is running on the computer, and we want to be able to communicate with the device. So first of all, I think we can go backwards today a bit because we already have the code and we already know it's going to work because I have already fixed it. So I think a good thing would be to go back and actually explore what is actually USB CDC, maybe even what is USB and what is USB CDC and all of those, and then we can kind of explore them and see what they are, and we can kind of start making our conclusions from there. So the first thing I'm going to do is I'm going to run the application that we had yesterday, and I think the best way to do it is I need to remove this and then I'm gonna do Ctrl R GCC main, but it has to have a Ctrl R GCC main, but then there's a C and then there's a dash L. I need to link USB, or maybe can I do something? Yeah, that's the one. So I need to link the USB library so that we can actually speak to the USB. So let's do that. It's built, and then I'm going to do sudo. So if I run it just by itself, it won't work because I need like permissions. I probably need to do udev permissions for this thing, but I haven't done it. So I'm just gonna shortcut it, and I'm gonna run it as sudo. So let's see, and we should get some errors if I. Yeah, we had a USB pipe error yesterday, and basically it wouldn't work. It doesn't really work. So the first thing we can do, I think, just to be kind of a little prudent, let's go back and let's revisit what is actually USB and what is USB CDC, and then we can come back to this device, and we can actually run the fix that I already found. The fix was actually a missing byte in the control structure that we were sending to the device. That was the only thing. We were just missing a byte, and that missing byte was making the thing fail, like it is failing right now, and that was, you know, breaking everything. So let's go back and find what is a nobody sausage. USB. USB. So USB IF, USB. So we can go through. We'll jump through a few bits of documents. So USB is a universal serial bus, and basically this is just serial communication between a device and a host. And serial communication means you can send a lot of bytes in one pipe, rather than having like several pipes for each bit of data. And basically serial communication is basically UART, if you can, or USART. And what happens with USB is the way USB works is the USB standard allows us to agree on if I send you this bunch of information first, if I send you this kind of bucket of information first, it means I am some sort of application. That's basically that's the difference between UART and USB. And then of course there's a few more lines. USB has USB pin out. USB has 4 lines, and I think UART has 2 lines. So there's 2 lines that are used for data, which are actually differential lines, and then there's 2 other lines that are used for control. So there's 4 lines here, as you can see. Yeah, good. So there's a power line, there's a ground line, and then there's a D3 and a D3 plus, D3 minus and a D3 plus. When you see them like this, D3 minus, D3 plus, and D2 minus, D2 plus. When you see them like this, it means these are differential signals, basically. Yeah, so differential signals are not single-ended signals. They're more you get data from 2 lines rather than 1 line. So it's not just 1 line that drops or 1 line that goes high, and then you get differential signals. So I just want to see an image. Yeah, actually I just saw one. There was a really good one there. So this is a very good image of differential signals, and yeah, all about circuits would be a good place to see. So look here, the difference between this and this gives you the actual bit. That's basically it. And the way this is designed is so that whenever there's noise on a line, both of these lines will be affected. And both of these lines, if both of the lines are affected by the same amount of noise, then the variation between both of them is the same. You see? So that's why they're twisted pair. It's called a twisted pair. And we do this in Ethernet as well. We do this in CAN bus. We do this in a lot of other signaling. And basically, it's there to prevent noise. Yeah, to prevent noise. Because if you look at this single-ended line and there was electromagnetic interference, this would be affected, but you wouldn't know. You see, you wouldn't have an idea of how much it was affected. But if there was electromagnetic interference here, if this was pushed down to say here, this would also be pushed down to here. So Excalibur. If anyone has any questions, you can ask them. Today is majorly an exploration. So let's remove all of this. I should start saving those images, and then let's take a thing and let's draw. So let's say we have a signal that goes. Okay, cool. I want to draw a free-form line. Can I get a free-form line? Am I allowed to? Yeah, something like that. So give me this and I'll draw a free-form line. Yeah. So let's do that. So this is a single-ended line. So that you either know this is a 1 and this is a 0, and then this is like a 1 and this is a 1 in here, and then this is a 0 in here, and then this is a 0 in here, and this is a 0 in here, and then this is a 1, and then this is a 0. And we're reading at the level of this. So we're reading at the level of here. This is the reading that we're using to tell us what bit we're being sent, what kind of data are being sent. Whereas with differential signals, you would have the same thing, 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 but then it would be different. It would be represented by two. Let's see. It would be represented by two lines. So there would be another one here, and this one would go low, and then it would go high again. You see, so something of like that. And what we're saying is, in here you're getting the difference. This differences between here and here. This is what is telling you what bit of data it is, and that this is designed so that if you had something called electromagnetic interference, there's people on the stream who are much better at that than me. Electromagnetic interference. This is why we have things like CAN bus for cars, because cars are big, the lines go long, and there's a lot of electricity moving in many places. And what happens then is that because electricity is moving, yeah, good. You can see here. This is a good example. So because a solar flare happened, and you can see video from C-SPAN got affected. Basically, noise happened somewhere, electromagnetic noise happened somewhere, or radiation happened somewhere, and then signals on Earth started getting affected. Basically, is what happened. And what we're saying is, in signals that travel long places, like a signal that is going from the back door all the way to the engine, it's going through a lot of other electrical signals, and all these other electrical signals might affect this. So differential signaling is developed to make robustness against that kind of stuff. Okay, cool. So that's what differential signaling is. Let's just find a good definition of USB. So Universal Serial Bus is an industry standard developed by the USB Implementers Forum, USB-IF, for digital data transmission and power delivery between many types of electronics. It specifies the architecture, in particular the physical interfaces and the communication protocols to and from hosts, such as personal computers and to and from peripheral devices, things like keyboards, mice, mass storage devices, intermediate hubs, and all of this. There's a lot of devices. Your webcam, the webcam that you're looking at me at from, anything that is using device USB. You might have noticed that this is where the name USB plug and play comes from. Usually whenever you have something that you plug into your computer's USB, you don't have to install additional drivers for it, because the thing that you plug into USB comes with drivers already. It comes with the drivers that tell your computer how to use it. And these drivers are implemented in a way, or in things called endpoints. Whenever we go to develop some USB some USB device class, we'll look at this quite detail. Hey Yasin, you're not too late. We just got started. It's literally been 4 minutes since we. What? Really? Has it been 4 minutes? It's been very short, I think. It's been 14 minutes basically. And what I'm really explaining right now is just what is USB and how does it work, and kind of like just breaking it down. We're not going to go into depth so much about what is USB. What we're going to try and look at today is an actual USB class and how it works, rather than what is USB. But basically, as we've read, the USB standard defines the physical peripheral device, the PHY, the physical interfaces, and then it also defines the communication protocols. And the communication protocols is like, if you send me this message, I will do this. If you reply with this, then this means XY to me and XY to you, and all of those things, and so on and so forth. So these are already defined. So devices like mice, like keyboards, like webcams. So your mouse and your Your mouse and your keyboard will belong to the HID USB class, so human interface device class. So this is something like a mouse, a keyboard, a touch screen, a touchpad, a game controller, a joystick. This is something that a human uses to communicate with a computer. And then, like the webcam that I'm using right now, is going to belong to the USB video class, which is UVC, USB video device class. So this is a webcam like the one that that is pointed at my face right now, and so on and so on and so forth. And in front of me, I am using a mic, and the mic I am using uses USB, and I think that belongs to the USB, and that is universal audio class, USB audio class, something like that. USB class. So USB audio class. So you see, there's a USB audio class that is used for so on and so forth. But so the thing we want to look at today is USB CDC. So what is USB CDC class? Let's look at that. So USB CDC class, this is actually quite short and I can read it verbatim, and then we can do a couple of questions, then we go into code. Or actually not even straight into code. We can open some documents and some code side by side, and then we're going to compare and contrast as we go along. So the USB communication device class is composite. Composite means it includes more than one thing. Universal serial bus device class, and it is mostly used for computer networking. Basically, you make a network from one computer to another computer. So my host computer is networked to this computer using this USB cable, and it's providing an interface for transmitting Ethernet or ATM frames onto some physical media, and it is also used for modems, serial ports, ISDN, fax machines, and telephony devices. So things like you can connect a phone, an SIP device or something to your computer, and you can use that, or you can a serial port, something like RS-232 or some other sort of serial port. Basically, you can use that with USB CDC. Devices of this class are also implemented in embedded systems, such as mobile phones, so that a mobile phone may be used as a modem or a fax or a network port. So you can use your phone as a gateway to use the internet, and the data interfaces are generally used to perform bulk data transfer. We're going to look at this shortly. Just now we're going to see it in the code. If you were here yesterday, you saw that I was writing and reading data from bulk endpoints, and these bulk endpoints are basically, if you think about networking, like the stream of pixels and the stream of audio that is leaving my machine into the internet or into some sort of network card, it comes out as bulk data. It's a lot of data. It's amalgamous, and it needs to be stuffed into some place. So there's like a pipe that is waiting for this, and so on and so forth. And then there's something called the abstract control model. So we have encountered something, these two acronyms. So it's USB CDC-ACM. So USB CDC is communications device class. ACM is the abstract control model. The abstract control model defined in the CDC specification can be used to implement a general purpose serial UART. So this is how basically we are doing things like this. Like now, you see here ACM0. I'm getting that ACM0 from a USB pin, or rather a USB connection, and the USB connection is getting to my computer, and it is basically pretending to be a USB CDC abstract control model echo, basically. You see, so this very message that we are getting from the device right now is using the USB class that we are trying to use. And then also on the other side, a USB thing is exposed that we are going to be using by ourselves. By the way, we can actually we can actually observe here. So because I can go and do, I think here I did picocom B. I can do picocom dash B. I think they said it's 9600. So here I'm looking at this baud rate 9600 or something. So picocom B 9600, and then I can do dev tty ACM SEM1. And if I do that, okay. Control A. Sudo. If I remember correctly, yeah. So you'll see here, yeah. I don't know if you see that, but anything I typed is echoed back. Anything I type into this thing is echoed back into the USB CDC sample that we're looking at, and that's because of this Zephyr USB CDC. Let's look. Yeah, CDC UR sample, and this sample demonstrates the use of a USB communication device class, abstract control model, driver provided by the Zephyr project. Received data from the serial port is echoed back to the same port provided by this driver. So, as you can see here, if I type 8, if I type G, if I type F, if I type R, if I type Y, it's just all echoed back. I type it, it's sent into a device, the device sends it back. It's an echo device thing. Let's finish reading that. So the abstract control model defined in the CDC specification can be used to implement a general purpose UART, and UART is, I think we all understand what UART is. It's universal asynchronous real time. What does UART mean again? A universal asynchronous receiver transmitter model. Okay. For example, an adapter cable, which is USB on one end and RS-232 on the other end, may present the USB end to the operating system as a CDC-ACM device, which uses the operating system standard CDC-ACM driver. Such an adapter provides a way to upgrade industrial equipment that uses RS-232, such as CNC machinery without changing the equipment's hardware or software. Most USB serial adapters do not use CDC-ACM protocol, but rather their own vendor-defined drivers and protocols which support more features. But there are a few adapters such as the PL2503 that do use it, CDC-ACM, and CDC-ACM is commonly implemented in software on microcontrollers such as the ESP and to provide a serial console. I've been shouting now for around, it's been 20 minutes, I think. So I'm gonna pause a bit. Can we do a couple of questions, and then we're gonna start exploring the code and the spec, because we have a spec and we have a code. Does anyone have any questions so far? Anyone have any questions so far? I know Yasin said there's a 30-second delay between me talking and you guys getting it. So I'm gonna give it 30 seconds. Okay, so it's been 30 seconds. Let's go back and actually look at what was happening yesterday. So Control C, Control A, Control X. And if I remember clearly, this needed to just be that sudo a out so that we can get it. And here you can see error during control transfer, libusb error pipe, and that was happening here. So and then that was happening here. So error during control transfer. Yeah, so basically let's go into our main and we can look through this. Whenever the main starts, we do a libusb init, and this we can actually go into here and we can start libusb. I think we can go into the documentation, the API, and then now we can start reading stuff. So how do I get see the application programming interface here? So now we the first thing we ran in main int return, and then we ran libusb init. What does this do? Let's look at it. Libusb init. Bartholomew probably already sees it and I don't. Libusb init ghi here. So libusb init, what does this do? Deprecated initialization function equivalent to calling libusb init without with no options. Okay, cool. This function must be called before calling any other libusb function. If you do not provide an output location for context pointer, a default context will be created, and it was already a default context and it will be reused. Then okay, cool. So it may be ignored or it may be null. As you see. So this just initializes the libusb library that we are using. Okay. And as I discovered, this was actually where my error was, because I did this and then I said debugging, but I never checked the control thing. But anyways, we'll get to that. So this is the first thing we do. We never get an error in initializing USB. We can actually do a printf here to tell us that everything is okay. Let's just make it verbose. Printf initialized libusb. Okay. Actually, no. Let's go to the fixed version of this thing. Let's go to the fixed version, and then let's fix that one. Git checkout. Fix. Okay. Git diff master So what has changed here? The things that have changed between the master and here is that nothing has changed here. libusb control transfer, okay. What has changed? What has changed? Transfer, dev h, and then this is transfer. Okay, so this looks to be the same, but I know there was a misspelling here. So this is what changed. Lib control transfer here. This is what I changed. This is basically all that changed since yesterday for this thing to work. So here, and then I was missing this. I was missing a byte here. Here's a byte I was missing, and I added a check here, and then this. Other than that, this gives us everything working. Just pausing for a bit. Okay, cool. So clear. So let's now actually envim this, and we can now explore the code properly. So the first thing I want to check is that whenever we've done init, let's do a print here to make sure that we show print f libusb initialized, and then n. Okay, cool. So that initializes libusb. That's it. So if we want to actually run it here, we can do a gcc first, and then we can do a sudo out, and then you can see libusb initialized. I don't want to keep going. Let's go to the next thing. Let's go to the next one. Libusb set debug. Let's find out what that function does and what it does. Libusb set debug. Deprecated. Says use libusb set option, or you use. But what does it do? Libusb set option. Here it is. Set an option in the library. Use this function to configure a specific option in the library. Some options require one or more arguments to be provided. Consult each option's documentation for that. So what we want to do is, I think, libusb option. Yeah, so here is the log level. Basically, what we are doing here is we are setting the log level to 3, set debug to 3, and setting the log level, what is the log levels? What are the log levels? So log level, yeah, what is the log level? So the 3 is set log level info. So let's actually do that. Let's write that here. Printf, let's do that. libusb log level set to info. Okay, so let's do that and acknowledge that that actually works. Let's go here and log it, and then that, and then we can see info here. So I didn't actually add a new line, so that I can always just return. And then this I can always just go no. No, it's fine. I'll leave it in. It's fine. We're actually just exploring the code, so it's fine. We know it works. We'll get there. So find the device that we actually want to device. libusb open device with vid PID. Okay, so let's go and look at that one. Let's go and look at that one. Let's go and libusb open device GHO libusb open libusb open. I've seen it. Open with vid PID. Hopefully it's not deprecated. Convenience function for finding a device with a particular ID vendor ID product combination. This function is intended for those scenarios where you're using libusb to knock up a quick test applications, and it allows you to avoid calling libusb get device list and worrying about traversing and freeing the list. This function has limitations and is hence not intended for real applications. If multiple devices have the same IDs, it will only give you the first one. So let's look at that. First of all, we have to go into Zephyr, I think. Zephyr project, Zephyr, and then in here we have to go into NV, and then I want to go samples, and then I want to go into subsys, and then I want to go into USB, and then I want to go into CDC-ACM, yes. And then I want to go here, and the first place I want to go into is the project conf. And the project conf, as you can see here, there's a PID that is defined here, which is 0x001. And then if I recall correctly, where was the let me go and find where the VID, the vendor ID is defined. I don't know if the vendor ID belongs to Zephyr already. I don't know if the vendor ID already belongs to Zephyr. So as you can see here, so there's a vendor ID. Oh, actually I can't check. So let's go here and copy that vendor ID. We did no. Let's see. The vendor ID. I think this is a test one. USB vendor IDs. So USB vendor IDs are like set or whatever. Okay. I search it? Come on. And the ID search. I just wanna. So they are assigned. You can use them. So vendor ID. Paste. Wow. What is it? 0 cross 2 FE. 0 cross 2 FE. FE3. Let us search. Who is this? I think this is a test one. Ah, there we go. There we go. There we go. So 0 cross 2 FE, it belongs to the Zephyr project, and it belongs to the Nordic semiconductor. So basically, this identifies that the vendor of this device is Zephyr, and it's made by the Nordic semiconductor. So, okay, cool. And then we have a product ID, which is 001, and 001 is 0 cross 001. Let's search that, and then let's see. I don't think there's a product that's been logged for that. Basically, I think this one was just defined. Okay, so we want to use this vendor ID and this product ID, and we are, as we've read from the documentation here, find with VID PID. It's convenience function for finding a device with a particular vendor ID and product ID combination. So that's what happens here. That, and then if dev age blah blah blah. If not, then else. Let's do an else here, and we can say found printf found device O2H and hex O2H, isn't it? What is it? Oh, X here, print, oh, X, yeah. X, something like that. Yeah, O2 hex, yeah. And then I want to do a O2 hex. And then here, and then I want to go like new line, and then what I want to say here is go like vendor ID, and I want to go product ID. Okay, cool. And then here, insert bit, and then and then if I save that, and I go build it and run it, if I save that, go build it and run it, and I run it, yeah, so you go, you see found device with 2FE301. Okay, so now let's go to the next point. Let's go to the next step. Now, since now we know what is happening here, I'll remove that. I'll close that one. That's the Zephyr code. We're not looking at Zephyr today. So the next thing we need to know is what happens here, because so this is done. Let's actually write some comments here, and then we can come here. Since devices are enumerated, are plug and play, they are attached, enumerated, and attached to the kernel driver as soon as they are plugged in. So in order to take over this, we have to disconnect the interfaces. And there's two interfaces, and I'll show you just now. Let's go here and we can find the interfaces. Control R, LS, USB, dash V, dash H, dash V, LS USB. I can actually go back until yesterday and I'll find it probably. I will find it, just hold on for me here. I remember actually finding it yesterday. How did we do it? Was it this? Let's use Control R, LS USB. Yeah, I think it was this. Cool. So this actually gave us what we wanted. So what I did there was I ran, let me look at it again. So what I did there was run LSBE. We can do LSBEH and see. So LSBEH allows us to run -S. We're allowed to run -S, and we provide the bus number and the device number, and then it only shows the specific shows only devices with a specific device and or bus numbers in decimal. So let's do LS USB, and then the device we actually want is this one, which is bus number 1, device number 8. Okay, cool. So when we do this, we see here, which I can actually zoom out, which will make it harder for you guys to see, but let me not zoom out. Okay, cool, whatever. I won't zoom out. So this is the beginning. We have a number of interfaces here, if you can see. So device descriptor, and then we will have some interface configuration descriptor, and then we'll have some interface descriptor here. If I do this, you'll see that it comes as 3. Grep interface descriptor. Oh, okay. Grep interface. So we have 2 interface descriptors, I think so. There's an interface descriptor here, and there's an interface descriptor here. So there's the communications abstract modem, and then there's the CDC data modem. So there's basically the control interface, and then there's also the data interface. And what we want to do here, what we want to do in the code is to detach both interfaces. We want to disconnect the interfaces from the computer, from the Linux kernel driver of USB. We want to disconnect those interfaces so that we can actually take over those interfaces from this code that we're writing. So let's actually look at these functions. If libusb kernel driver active, so let's actually go see what is that. Libusb kernel driver active. DK if libusb kernel driver active. Yeah. Determine if a kernel driver is active on an interface. If a kernel driver is active, you cannot claim the interface, and libusb will not be able to perform I/O. This functionality is not available on Windows. Anyways, I think this explains very clearly. So if the kernel driver is active, if the kernel driver is active, like the one we just naturally plugged it into, then we try to do some communication with the device, it would never work. Okay, so in order for us to do it, we have to disconnect the kernel driver from that device, and then once we disconnect the kernel driver from that device, we can actually now attach them as ourselves, and then we'll see what happens now. So look at here, detach a libusb detach kernel driver. Detach a kernel driver from an interface. If successful, you will then be able to claim the interface and perform input output. Again, not available on Windows. Note, libusb itself also talks to the device through a special kernel driver. If this driver is already attached to the device, this call will not detach it and will return libusb error not found. Okay, cool. So let's look at the drive. So we know there's two interfaces. We can see them here. There's an interface descriptor here, communications, abstract modem, and then CDC data. Okay. So there's the control one, the thing that controls the whole thing, and then there's another one that is used for sending data. And all devices will always have an interface for control and some few more. Okay, and some few more. Like if we go into LS USB, let's pick up something else. Not that one. Instant optical mouse. So that is bus 3. Device 3. Let's look at how many bus 3, device 3. Let's see, 3, and you can see. So this only has one human interface subclass. See, so it has a number of interfaces actually. BNAM interfaces to 1. So a lot of them will either have like just the control one, or they will have the control one and something else. And we can actually look at, I think let's look at the UVC camera. There should be a UVC camera somewhere. I should have a microphone somewhere here. Use keyboard, no. Optical mouse, no. Foundation hub, Realtek. Yeah, let's look at this. So 1.6. This is my microphone. Microphone. 1.6. How many interfaces do we think that has? As you can see, this has a lot of interfaces. It has 4 interfaces. It has a audio control interface, audio streaming interface, this is probably channels. And then also at the end, it has a human interface device. So as you can see, this is something, this one is also a composite device because it has more than one device in the same thing. That's why sometimes you can plug a USB thing in and it has a drive for one thing and a drive for another thing, and it also acts as something else. Let's look at another one. I'd like to look at my webcam. Optical mouse, keyboard, root hub, Aura. I thought I would have a webcam somewhere here. This is audio. This is hub. This is a hub. This is a ST. This is a keyboard. Probably this. Aura LED. Bluetooth radio. No. Wow. Let's look at device 1, 2. 1, 2. So this is a human interface device, and that's it. I'm very shocked that my webcam is not coming up here, because I guess it's already enumerated in dev video, so that's why it's not. I understand. So probably OBS has taken over. Just the same thing I'm doing right now. OBS has taken over from the kernel drivers, so I can't see the webcam. What happens if I kill it? Okay, I'm not gonna kill it because I would have to set up a lot of things after, but I think if I kill it, then it will show up on LSUSB, which is because let's actually finish our whole application and see. But we can always find that out by doing this, by doing sudo a out. If we do that, yeah, if we do that and then we do LSUSB, do we get the Nordic device? It is there. Okay, Okay, so fine. But basically what we just did here is we're going through the interfaces. There's two of them. That's why there's 0 to 2. There's two of them. We're going through them and we are detaching them. And then after they're detached here, if this succeeds, after the detachment it succeeds, we want to do a libusb claim interface. So what does claim interface do? Claim interface. Libusb claim interface. Okay, cool. Yeah. If anyone has any question, please feel free to interrupt me and stop me because I'm having too much fun. I'm just exploring code. If anyone has any question, feel free to tell me. Feel free to interrupt me and stuff. I'm pausing a bit right now for a drink of water, and then we go on from there. Any questions? Any questions? No questions. So, libusb. Claim an interface on a given device. Yeah, I think you can see that. Claim an interface on a given device handle, and you must claim the interface you must claim the interface you wish to use before you can perform input-output on any of its endpoints. It is legal to attempt to claim an already claimed interface, in which case libusb just returns 0 without doing anything. If auto-detach kernel driver is set to 1 for a device, then the kernel driver will be detached if necessary. On failure, the detach error is returned. Claiming of interfaces is a purely logical operation. It does not cause any request to be sent over the bus. Interface claiming is used to instruct the underlying operating system that your application wishes to take over the ownership of the interface. So as you can see there, we are just telling Linux, or we're just telling the operating system that we are now taking over this device. So let's actually put some label in the code there and see, and say if all of this goes through, if that error does not occur, print f, and we want to say this, and we want to go device O2x has been claimed. Okay, and then here we just want to pass in product ID. Okay, cool. So now we're getting to the place where we had an error yesterday, but I'm gonna do a build here. I'll get the build command from here. From here. No. What is happening? Oh, okay, yeah. So I just want to do this. I just want to do a build here, and then in here I want to do sudo a out, and what we can see here is libusb initialized. There we go, and then control-C, libusb initialized, and then libusb log level set to the info. Found device 2FE301. Device 01 has been claimed. So let's keep going with the code now. Let's go keep we're actually almost done with the code, so we're almost done exploring what this code does. So now the first thing we need to do is talk to the control interface of the device that we've just claimed. And the control, there's a few interfaces that you can expose. You can you're legally required to expose control interface, and then depending on whether just a control interface is enough, then that's all. But if you need more interfaces, like we saw with the microphone, like we saw with the webcam, like we saw with the keyboard, if you need more interfaces, you can also expose them so that the device can be used in a certain way. So the first thing is we want to do a control transfer. libusb control transfer. What does that do? What does that do? libusb control transfer. Yeah. Perform a USB control transfer. The direction of the transfer is inferred from the BM request type field. BM request type field here. This one. BM request type field of the setup packet. The W value, W index, and W length fields should also be given in host endian for byte order. Okay. So W value, W index, and W length should be given in host endian format. So here you go. And then what is the last one? The timeout. Timeout in milliseconds should before wait should before giving up. For unlimited timeout, use 0. So this is the device handle. Yeah, we're sending a device handle, and then the first thing we send is a BM request type, and I think we can find that out from the spec itself. I do have the spec somewhere here. USB CDC docs. Okay, cool. Control F, BM request type. BM request type, BM request type. So 001B. So that's that. That's, I think it's 01. BM request type, and we're doing, what are we sending? We're sending control status 0 cross 21 control transfer. Oh wait, 0 cross 21. 0 cross 21. So that is the 0 cross 21, and I want to do hex to binary. Convert, it's 001 0001. So this looks to me to be this. So 001 001. So here, send encapsulated command. Yeah, you see? And then the W value is supposed to be 0. The W index is supposed to be the interface. And then the length is amount of data associated with this recipient, and the control based. So here we're sending a encapsulated command, and then this now happens to be what? This, what value is this? O0 or x22 or x22 or x22. Where is the documentation? Or x22, leave USB, or x22 is the B request field. The request field for the setup packet. So we want to see what is the request field. B request. Sorry. It's directly a B request. B request code, I think. B request, yeah. So B request code is send encapsulated command. Oh, what does that mean? So this is the 0 cross 22. Okay, fine. And then the W value here is 0, and then the index is the interface. So, and then the data is what we are actually sending, control based command, and then the length and the timeout, which you already have here. So that's the index. That's this is now the third one. What is the third one again? It's the value. We're doing an ACM control, but we're sending a DTR and an RTS control command. ACM control DTR. We want to find out what those are. ACM control DTR RTS ACM control DTR. What is that? So these are, what are they? DTR. Come on, somewhere it's defined. Somewhere there's a definition. The USB host controls the line control, RTS and DTR pins. So these are pins and the break signal and such. So the line control pins, line RTS and DTR pins. And this is 7/7. So these are pins that the host controls in order for us to communicate the thing. So basically here, what is happening here in our code here is that we are setting both of them because we are doing that or auth and then 00 now. Now this is the no data length value, and then that's the timeout. Basically now what we've done is we've sent an encapsulated command, and then the next thing we need to do is 0x80. Whoa, so this is the data. So what is that but 0x20? 0x20. The third one, what is the third one? BM request. BM request. B request. B request. Encapsulated command. Send encapsulated command. Okay, so that's that. 00. But that's the, no, that's the third one. So oh yeah, okay. B request. B request type. Oh yeah. So because this returns that B request type, B request code. I have a feeling they're all defined somewhere else. Okay, 21. So 21H. Yeah. Get line coding. So here we're getting the line coding. I think so. Because that's the actual request code that we're sending here. As you can see, get line coding 21H, which is the one that we're sending here. So we are trying to tell that we want the device here to tell us the line coding, and then the line coding is what we're asking for, and then the next thing we're asking for, which is the request itself, is the 20H. 20H set line coding. Okay, cool. So and then we're doing get line coding, set line coding. No. Would we do that? Or would we say control transfer get line coding, set line coding, and then we send this whole packet here? This is the encode. Yeah. You can see here we're setting the encoding. We're setting the RTR and DTS encoding for the whole communication packet that we're going to do. So we're telling the USB how to handle these pins and how to what to do with these pins. When we get to a point that we are writing actual USB drivers from the device side, this is all going to plug in and make quite a bit of sense, because then there's going to be connection between the data that we're sending out and bringing in. Okay, cool. So here we're going to say, come here and say print f line coding set, and then that's a new line, and then that's that, and then that's that. Okay, cool. Okay, cool. So that's the meat of the thing done. That is it. That we've done all of this. We've done all of this control stuff. We've set it up. Now we're ready. Now we're actually ready to talk to the thing. We're ready to go back into the device, and now we're ready to start sending that data and receiving the data. So we make a character buffer of 65, and then we make our length, And then now what we do, we want to do a write character, but this is a function that we defined before. What does that do? Define a write to a device. This is whenever we want to write to the device, we need to write to by writing to EP out. So we need by performing a bulk transfer to EP out. That's how you write to the device. Okay. So we get an actual length. This is just a definition here, and we say int return is equals libusb bulk transfer. Well, let's look at what that actually does. Libusb bulk transfer. Libusb bulk transfer. Perform a bulk transfer. The direction of the transfer is inferred from the direction bits in the endpoint address. So the endpoint address, which is defined here, endpoint address here, which is defined, EP out here and EP in here. So EP out is to the device from the host, and EP in is to the host from the device. So and then what we want to do is we pass in the developer handle, the device handle, and then we pass in an endpoint, which is the thing we're sending here, our AP out address, and then we want to pass in the data that we're sending, which is the character array the character that we want to send, and then the length, which is 1, and then the transferred length. This is a pointer that will be set by libusb that tells us how much has been transferred to the device. Okay, so this is actually what has been transferred, and then this is and then 0 is the timeout, basically how long to wait before sending this data. Okay, so this actually, all this does is it sends data to that defined read from device by writing by collecting from EP in. Okay, let's go again. What happens here? So we make an actual length, and then we do a bulk transfer, and then this one goes to the EP in address. We say we want to read. This read characters takes a pointer to some data, and then we pass in that pointer here, and then we say it takes a pointer and some size to read from. So we say that data, that size, and then the actual length is it's the same as the one that we were doing for sending. It's just this is the one that comes back, and then we give it a 1000, which is timeout in what? Timeout in milliseconds that this function should wait before giving up due to no response. Okay. And then we go and look at if the return is libusb error timeout, then we say there was a timeout that occurred, and this is how much came back, and then we return a -1, which is an error. And then else if it's another error, we print out to the std error output, and then we say we got an error while waiting for the characters. Otherwise, we return the actual length. And then let's go and actually look at how this is used. So we make an unsigned character buffer of 65 characters, and then we define a length that we're going to be using, and then we send let's actually send this to become something like J or L. Let's change that, and then we say read characters buffer, and then we say give us 64 characters. Wait. Read characters. What does 64 do? This is the size that we want to read. So read characters into buffer 64. Okay. So we want to read from 0 to 64. That is 65. That can fill this. Okay. So we want to read those, and then we say buffer length is equals buffer length is equals 0. Wait. So buffer length is equals 0. So the character in read characters 64, but the character in length, so the 64th character, we want to set it to 0, and then we want to print out received s buffer. Okay, yeah. So we want to put into buffer whatever we get in, and then we want to print a new line, and then we want to sleep 1 second, and we want to do it again. And if ever we come out of this, we want to libUSB release. So we can have some rule here that says something like if the serial device ever sends character sequence XXXYYY, we can release the device. But at the moment we don't do that. But let's look at libUSB release interface. What does that mean? What does that do? libUSB release interface. Release an interface previously claimed by libUSB. So this is now like we're letting it go. We're letting it go because we took it from the operating system. We're done doing what we did with it. Now we're giving it back to the operating system to do what it needs to do with it. Okay. And then after that, in case we have a label here called out, which we have called a few times. So out happens, go to out. So if we do get an error while finding the USB device, we will go to out. And then if we do get an error when we are claiming the device, we will also go out. And the label here is out, and we're saying if the device is there, we want to do libUSB close. And what does libUSB close do? libUSB close, what does it do? libUSB close the device handle should be called on all open handles before your application exits. Internally, this function destroys the reference that was added by libUSB on the given device. This is a non-blocking function. No requests are sent over the bus. Cool. And then we need to call libUSB exit. What does that do? And then we need to call libUSB exit, and I think we can infer in libUSB exit, here it is, the initialize libUSB should be called after closing all open devices before your application terminates. And in such a way, if we do all of that, what happens? Let's go here and see. So let's do it here, and then the first thing I want to do is actually build it. And once I build it, I want to run it, and then there you go. libUSB initialize, but this is sending G. Why? Means I haven't saved. Let's build it again, and then let's go and run it. Yeah. Oh, that's, whoa, there was something living in the buffer while that was set. So libUSB is initialized, libUSB log level is set to info, found device 2FE E301, device 01 claimed, line coding set, and then we received a G, we received an L, we received, so you see, we're just logging every time we receive an item from the device. But basically, and in a short way, that is how libUSB host application works. As we've gone through the API, we've built through it, and we've seen what things they do and what happens in the code. And here we have some working code that actually sends messages to the device and speaks to it. That was really awesome. It's really cool to actually have something working and to spend most of the time actually like exploring the actual lines of code in the solution. Yeah. Thank you all so much for coming to today. Thank you, Yassine. Thank you, Bartholomew, for coming to today. That was really exciting. And I hope to see you guys around and other times. And I hope we find more people. And this is quite awesome. As always, my name is Zach. And if you've stayed this long and you want to support my work and you want to support my streaming and my research and my development, you can always check on the description. There's a link to a Discord community. Join us and do stuff with us. And then also there's a link to a GitHub sponsors page where you can actually help me buy more devices, get more time, basically get more computers so that we can work on more of these devices all of the time and explore this esoteric, embedded, and deep computing things. Thank you so much. My name is Zach, and I bid you all to be courageous and to be daring. Thank you, and cheers. If anyone has any questions before I go, you can ask them. Thank you so much. I don't think that anyone does. So cheers. See you.